welcome to the course on linear programming. We have seen linear programs, we have seen some linear algebra, specifically how the solutions of Ax equal to b look. Today we will see that that is not good enough and we have to introduce the concept of convexity theory. But before I start, what happened here, right? So, the idea was that the solution set of this was easy to describe, right? If you remember, I take the matrix A and I can do Gaussian elimination, right? So, if I do Gaussian elimination, it turns out I will have this kind of a structure where I do not know this will be some entries, but what do I know? These are my leading variables and these are my free variables, right. So, let us just call the leading variables x1 to xk and the free variables xk plus 1 to xn, right. So, what do we know? If I want to create any solution of Ax equal to b, then how can I do it? So, first fix up anything, any value of free variables, right. So, this can be obtained by two steps. First, and then once you fix up these values, this will determine the value of x1 to xk uniquely, and this is given by these coefficients, right. So, sounds good. This means there is no restriction on xk plus 1 to xn, right. This is anything in r to the n minus k. I can fix these values as whatever I like, and then I am by arranging x1 to xk in a certain way determined by these coefficients, I am sure to get a solution of Ax equal to b, right. Other way to say it is write x1 to xk as linear combination of xk plus 1 plus some constant c1, some coefficient here, some coefficient here, similarly ck. But once I know this, I can substitute this in C transpose x, and then I have got a function of the kind, was it minimized? Okay. These coefficients will change plus some constant c, and there are no constraints remaining, right. It is just optimizing this linear function. And now my life is easy. This is going to be minus infinity if any of these are non-zero, because then I can make sure that going in that direction I can make it negative. There is a trivial case, you have to remember that if all of these are 0, then that means for any solution the objective function is c, okay. This is all. So, this basically means this is very simple to solve, because even in a very bad case you can do Gaussian elimination in order of n cube, okay. Order of n cube is a pretty good bound on Gaussian elimination, probably do better, but yeah. So, that means we can solve this problem very easily. correct? Great. So, this direction did not help. It shows us things only become interesting when I have this constraint, right? Otherwise, there are not many applications also. It's this constraint which is making this linear program interesting. And you remember what we were trying to do? We were trying to learn linear programming, and now we tried a simplification that is too simple. Now you want to see, oh, life is not that simple, but can we still get some more information, right? So, when our feasible space was a vector space, right, Ax equal to b, the solutions of Ax equal to b is a some kind of a fine space. That's easy, that's not very difficult, but that's not going to be the case. So, the question is there still some structure of feasible space which allows us to solve it easily, right? So, the question in other words is, how does feasible region change with x greater than equal to constraint? Okay. And when you can't solve a problem, the best thing to do is, now you are not in linear algebra, right? We have come out of linear algebra. So, Gaussian elimination is not the answer to everything. Yes, so that we tried, and generally it is good to look at small subcases, right? You want to simplify the problem. There are many ways to simplify a problem, remove an assumption, or now in this case, since you want to understand the structure, let's at least see what happens in 2D or 3D. So, now let us say in 2D, that is the simplest. I have a program, so minimize something, I do not care, I am interested in just the feasible region. Let us say this is the problem. Right? If this is the case, and there is some line like this, right? So, what is my feasible region? No, just the line segment, right? My feasible region is just this, right? And now this is not a vector space. But then what is it? It is still nice, right? It's still a line segment, it's not completely unstructured or something. So, what do we know about line segment? It's actually a convex set. And once we observe this, we remember Minkowski and say, oh, in 1900 he has done so much about convex sets. Let us learn from him. Let us see what has been done and see if we can apply those principles in our problem. And this is what we are going to do in next week. So, we are going to learn convexity, we are going to learn about convexity theory, and immediately we will see that an algorithm pops out because of the structure already known of convex sets. Sounds good? That is the plan. Our target becomes learning convexity theory. How many people have studied convexity theory before? Some idea? Okay. So, convexity theory is study of convex sets and convex functions. And if you read this, what you realize is most important thing is this word convex, right? And the first thing we will start with is convex combination. And again, the idea is to describe this line segment instead of this line, right? So in a plane, how do you write if you are given vectors, let's say x1, x2, or let me, these are two vectors in R square, what is the line passing through it? Lambda where lambda is that okay with everyone? Correct? What is this? This is a linear combination, right? And then that means in 2 dimension this is, what is this? What is the shape? Plane, mostly a plane, right? Except some trivial cases when these are linearly dependent, right? Good. So first thing was, from linear combination, if I wanted to come from the entire plane, if I wanted to restrict my attention to a line, I do this. Okay, so this is a line, this is a plane, and how do I get a line segment? Anyone except Dev? Thank you. Right. So it is lambda x1 plus 1 minus lambda x2 such that lambda is in 0. Right? And now, when you look at all this, there should be one more combination which should come to your mind. What is that? So this is called convex combination. This is going to be important. What is the remaining combination? If you see these cases, don't think of geometrically. Look at these three. So now I started with any general lambda 1, lambda 2. I put one kind of constraint. I put other kind of constraint. What kind of constraint is remaining? So this was a plane. This is the constraint that summations are up to 1. This is the constraint that both are positive. If you mix these, you get this. This is called conic combination. Okay? And how will the conic combination look? Right. Suppose this is a point x1, this is a point x2. The conic combination, what will be that set? What will be that set? You can tell me. Definitely this point is going to be there. This entire line is going to be there. You can convince yourself of that, okay? You can look at this. And now, because I talked about convexity theory, convex sets and everything, it seems like this is the most important thing. But I assure you, all 4 are going to be important for us. All 4 kind of combinations are going to be useful for our study of linear programs. And the reason is pretty simple. If you look at constraints, something like A transpose X equal to B, this is going to be an affine set. If you look at, this is a right. So all these shapes, all these combinations are going to arrive when we are going to study linear programming. Make sense? And this is what we are going to do, study these combinations. That's the plan for today. Okay? Just to make sure that you understand what is going on, which statement is correct. Don't discuss. Let's take a vote. 4 options, right? None of that is correct. Both of them are correct. First one is correct. Second one is correct. That is why India does not have a good political system, because nobody votes. Like out of 12 people, only 3 people voted. What the hell? Okay, think about it. I will give you some time, but everyone has to vote. Bring out your pen and paper. Let's good. Okay. Very good. So the first question to ask is, we have seen an example of an affine set. I told you that line segment is convex, a line is affine, right? So at this point you can only answer this in terms of examples. Okay, but an affine set is something which has all its affine combinations. A convex set is something which has all its convex combinations. Oh, I just told you. I had written down these ones. Okay, let me just write it. So the way to remember it is, linear combination is affine, the constraint is lambda 1 plus lambda 2 equal to 1. Conic is lambda 1 lambda 2 greater than equal to 0. Convex is which basically means it lies between 0 and 1. Okay? The A transpose X equal to B. No, the space you get is not a plane, you get a line, right? For example, when it was 3x plus 2y equal to 5, in the 2 dimension, did you get a line or did you get a plane? You got a line, right? So it's only an affine combination. Don't get confused by when I say Ax equal to B, are you thinking of it in terms of, and you are saying that's why this is a linear combination? No, here what you are saying is any x1 to xn which satisfy this equation are going to be in your feasible set. It is not saying that you have x1, x2 and xn are vectors here and you are taking any possible linear combination here. That is not what you are saying, right? So, do not get confused, and this is actually very important. It is a very nice question because we will see this duality in terms of, oh, it is a linear combination, affine combination, or I can describe it in terms of equations. Both sides are very important. For a geometric picture, oh, it is a linear combination or an affine combination. But if I want to study it, then I also want to see the equivalent way in which it can be written down as a bunch of equations, and this we will see. Okay, so this is very nice. This confusion is natural to arise, but we should remember. So all these sets we will describe in almost two ways. Okay, so now you know an affine set is something which contains every affine combination. A convex set is something which contains all the convex combinations. Now let's vote. Okay, how many for one? One vote. Okay, both incorrect. People are guessing. How many for three? There is influence. You are not allowed to, either you would not vote or you will vote twice. There is something wrong with the youth in this country. 1, 2, 3, 4, 5. You voted already, I know. Yeah, and you said that is obvious, no? No. This is the correct answer. Given that out of 15 people, only 5 got it right, it is definitely not obvious, right? So what is happening here? A line segment, remember, a line was affine. Is it convex? Why not? Take any 2 points, take anything here. Its convex combination is inside that line? Yes, no? Convex combination, look, it is the line segment between the 2 points, right? That we described. Remember I said what is a line segment? It is a convex combination of those 2 points, right? So if you take a line, you take any 2 points, the line segment between them is part of this. So it also contains convex combination. So affine implies convex, and a line segment, this is convex but not affine. Why? Because the affine combination of these 2 points will be the entire line. And you can make an argument, you know, oh, the affine combination condition is stricter, convex combination condition is weaker, and I always get confused. You can do that and you can figure out and say that, oh, the condition for this is weaker than the condition for this. Sorry, the other way. This is the stronger condition, this is the weaker condition. So if the weaker condition is true, this is fine, right? But if you get confused, line segment line is your friend. This weaker and stronger is always confusing for you. But yeah, if you are very, very precise and if you are not drunk, then even the weaker and stronger will make it work. And for the record, I am not drunk now. Okay, good. So affine combination, all those are making sense now? Okay.